Physics is the fundamental science that underpins our understanding of the universe. It provides the most basic description of physical reality, encompassing everything from the smallest subatomic particles to the largest cosmic structures. This includes quarks and leptons, the building blocks of matter, as well as stars, galaxies, and the large-scale structure of the universe. Physics principles apply universally across these scales, making it the cornerstone of scientific knowledge. Physics operates across diverse scales, each requiring specific tools and concepts to understand the physical world. These scales span from the incredibly small subatomic realm to the vast cosmological scale, covering over 40 orders of magnitude. This hierarchical structure reveals how fundamental forces and particles give rise to complex structures, from atoms to galaxies. The subatomic scale, measuring about 10 to the power of negative 15 meters, is the domain of particle physics. Here, we encounter fundamental particles like quarks and leptons, governed by quantum mechanics and the Standard Model. Tools such as particle accelerators and detectors like those at CERN's Large Hadron Collider probe these tiny dimensions, revealing the building blocks of matter and the forces that bind them. Moving up to the atomic and molecular scale, around 10 to the power of negative 9 meters, we find atoms and molecules. This scale bridges quantum and classical physics, where electrons orbit nuclei in probabilistic clouds rather than fixed paths. Concepts like chemical bonding and molecular interactions emerge here, studied through spectroscopy and microscopy. Understanding this scale is essential for chemistry and materials science. The nanotechnology scale, ranging from 1 to 100 nanometers, represents a mesoscale where quantum effects begin to influence macroscopic behavior. At this level, properties like surface area to volume ratio become critical, enabling innovations in materials with unique electrical, optical, and mechanical characteristics. Tools such as scanning tunneling microscopes and atomic force microscopes are indispensable for exploring and manipulating structures at this scale. The human scale, approximately 1 to 2 meters, is our everyday experience where classical physics dominates. Newtonian mechanics, fluid dynamics, and thermodynamics govern motion, heat transfer, and everyday phenomena. This scale serves as a reference point, allowing us to relate microscopic and macroscopic behaviors. Concepts like friction, gravity's effects on human motion, and energy conservation are directly observable here. The astronomical scale spans from 10 to the power of 6 meters, like small asteroids, to 10 to the power of 21 meters, encompassing entire solar systems and galaxies. Here, gravity dominates, and relativity becomes significant for high-speed phenomena. Telescopes, both ground-based and space-based, like the Hubble and James Webb, reveal stellar evolution, planetary systems, and galactic dynamics, governed by Newton's law of universal gravitation and Einstein's general relativity. Finally, the cosmological scale, reaching 10 to the power of 26 meters, encompasses the entire observable universe. Concepts like the Big Bang, cosmic expansion, dark matter, and dark energy are central here. Observations from satellites measuring the cosmic microwave background and large-scale structure surveys provide evidence for these theories. Understanding this scale requires integrating particle physics, gravity, and thermodynamics to explain the universe's origin, evolution, and ultimate fate. The study of the smallest building blocks of matter provides crucial insights into the vast structures of the universe. Elementary particles like quarks and leptons, along with their interactions through fundamental forces, determine how galaxies form, evolve, and cluster on cosmic scales. For example, the strong nuclear force that binds quarks into protons and neutrons is the same force that powered the Big Bang's initial expansion, setting the stage for all subsequent cosmic evolution. The electromagnetic force governs atomic structure, which in turn influences stellar formation and the chemistry of planetary systems. Even the weak force, responsible for radioactive decay, plays a role in stellar nucleosynthesis, creating the heavier elements that make up planets and life. This bottom-up approach shows how microscopic physics scale up to explain the universe's large-scale behavior, from the formation of the first stars to the distribution of galaxy clusters across billions of light-years. Conversely, observations of large-scale cosmic phenomena provide essential constraints on the properties of elementary particles and their interactions. The cosmic microwave background radiation, a remnant of the Big Bang, reveals details about the universe's early moments, including the behavior of quarks and gluons in the quark-gluon plasma that existed microseconds after the Big Bang. Measurements of galaxy clustering and the large-scale structure of the universe help us understand dark matter particles, which interact weakly with ordinary matter but dominate cosmic structure formation. The abundance of light elements like helium and deuterium, created in the first few minutes of the universe, provides precise tests of particle physics models, particularly the number of neutrino species and their masses. Even the accelerating expansion of the universe, driven by dark energy, constrains theories of fundamental forces and particle interactions at the highest energies. This top-down approach demonstrates how cosmological observations refine our understanding of particle physics, often revealing phenomena that are difficult or impossible to study directly in laboratory experiments. This interplay creates a truly symbiotic relationship, where advances in one domain drive progress in the other. A striking example is the prediction and discovery of the Yule particle in the 1960s. By organizing known particles according to their quantum numbers, like strangeness and charge, physicists identified a gap in the pattern that required a new particle. This theoretical prediction, based on symmetry principles derived from particle physics, was confirmed experimentally at Brookhaven National Laboratory. Such discoveries illustrate how the quest for completeness in small-scale physics leads to breakthroughs that validate our understanding of fundamental symmetries. Today, this symbiotic approach continues to drive research, with cosmological observations from telescopes like the James Webb Space Telescope informing particle physics models, while laboratory experiments at facilities like the Large Hadron Collider provide data that refines our cosmological models. This interconnectedness is what makes modern physics research so powerful and productive. The ultimate goal in physics is to develop a theory of everything, or TOE, that can explain all aspects of the universe. This ambitious pursuit seeks to unify all known branches of physics into a single comprehensive framework. Currently, physics is divided into separate branches that work well in their domains but don't fully integrate. These include classical mechanics, which describes everyday motion and forces, relativity, governing high speeds and gravity, and quantum theory, explaining the microscopic world of particles and energy. A theory of everything would merge these branches into a unified framework, explaining how they interconnect and derive from fundamental principles. While this remains a significant challenge, several obstacles stand in the way. Quantum mechanics and general relativity, for instance, are incompatible at certain scales. Additionally, phenomena like dark matter and dark energy, which make up most of the universe, are not accounted for in our current models. Gravity, described by relativity, has not yet been successfully quantized. Ongoing research is pursuing several promising approaches. String theory proposes that fundamental particles are actually tiny vibrating strings in higher dimensional space. Loop quantum gravity treats space-time as made of discrete quantum loops. Recent advances in quantum simulations, using processors like Google's Sycamore, have successfully modeled black hole entropy, providing insights into potential TOE frameworks. These efforts are gaining traction and could lead to breakthroughs in the coming decades. Looking ahead, the development of a theory of everything may require advanced technologies. Next-generation particle colliders and space-based detectors could provide crucial data. Hybrid quantum classical computers are expected to simulate complex TOE candidates. AI will play a key role in analyzing vast data sets and theoretical models. While no unified theory exists yet, experts estimate that a breakthrough could occur within the next 50 years. The pursuit of a theory of everything represents humanity's quest to understand the universe's deepest secrets, bridging the gap between the very small and the very large. Reductionism is a powerful approach in physics that suggests we can understand complex systems by breaking them down into their most fundamental components and studying how those components interact. In physics, this means analyzing the behavior of elementary particles, the building blocks of matter, to explain phenomena at all scales, from atoms to galaxies. The Standard Model organizes these particles into categories: quarks, leptons, gauge bosons, and scalar bosons, each with specific properties like mass, charge, and spin that determine how they interact. While reductionism successfully explains many physical processes, it has limitations. Complex systems can exhibit emergent properties that cannot be predicted solely from the behavior of their individual components. For example, the properties of water emerge from hydrogen and oxygen atoms interacting, but cannot be fully understood by studying those atoms in isolation. This interplay between reductionism and emergence is key to understanding the universe's complexity. At the heart of all ordinary matter in the universe are three fundamental elementary particles: up quarks, down quarks, and electrons. These particles, discovered through decades of experimental physics, form the basis for everything from atoms to stars. Up quarks and down quarks are the fundamental building blocks that make up protons and neutrons. Protons contain two up quarks and one down quark, giving them a positive charge. Neutrons consist of one up quark and two down quarks, making them neutral overall. Let's examine their key properties. Up quarks carry a charge of positive 2/3 and have a mass of about 2.3 million electron volts over c². Down quarks have a negative 1/3 charge and a slightly heavier mass of 4.8 MeV. Electrons, while not quarks, complete the trio with a full negative charge and a much lighter mass of just 0.511 MeV per c². When up and down quarks combine, they form the protons and neutrons that make up the atomic nucleus. Protons and neutrons are bound together by the strong nuclear force, creating a dense core at the center of every atom. A proton consists of two up quarks and one down quark, resulting in a net charge of positive 1. A neutron has one up quark and two down quarks, giving it 0 net charge. The nucleus is incredibly small compared to the atom, containing nearly all its mass. Electrons are bound to the nucleus through the electromagnetic force, creating the familiar orbital structure of atoms. While the nucleus is dense and contains protons and neutrons, electrons occupy the vast empty space around it, forming electron clouds or orbitals. These particles interact through four fundamental forces. The strong nuclear force binds quarks together to form protons and neutrons. The electromagnetic force keeps electrons orbiting the nucleus. The weak nuclear force governs radioactive decay, while gravity plays a negligible role at atomic scales. Together, these fundamental particles create the atoms that form all matter. Different combinations of protons, neutrons, and electrons give rise to the 118 known chemical elements. From the simplest hydrogen atom with one proton and one electron to complex molecules and materials, all emerge from these three basic building blocks. Through their interactions via fundamental forces, up quarks, down quarks, and electrons construct the atoms, molecules, and materials that make up our universe. This simple foundation underlies the incredible diversity of physical structures we observe. Atoms are the fundamental building blocks of matter, each consisting of a nucleus with protons and neutrons, surrounded by electrons. When atoms combine, they form molecules through chemical bonds. For example, two hydrogen atoms and one oxygen atom bond to create a water molecule, demonstrating how simple atomic interactions lead to more complex structures. Molecules then assemble into more complex structures. In living systems, biomolecules like proteins, lipids, carbohydrates, DNA, and RNA organize to form cells. A cell is the basic unit of life, with organelles such as the nucleus containing DNA, mitochondria for energy, and the cell membrane maintaining structure. This organization shows how molecular interactions create functional biological units. Cells combine and specialize to form tissues, organs, and ultimately organisms. This creates a hierarchical structure of complexity. Atoms form molecules, molecules form cells, and cells form organisms. Each level builds upon the previous, exhibiting emergent properties like metabolism, reproduction, and consciousness that arise from the interactions at lower levels. Physics provides the foundational principles underlying these processes, such as the electromagnetic forces that govern chemical bonds and the thermodynamic laws that regulate cellular energy. However, while physics explains the physical mechanisms, the emergent properties of life, like self-replication and adaptation, require biological sciences for complete understanding, as they cannot be fully reduced to physical laws alone. Emergent properties are characteristics of complex systems that arise from the interactions of their components, rather than from the properties of individual parts alone. These properties cannot be predicted solely from knowing the fundamental building blocks. They emerge from how those parts interact. Consider crystal structures in physical systems. Individual atoms behave according to fundamental physics, electromagnetic forces, quantum mechanics. But when arranged collectively, they form crystal lattices with properties like hardness, conductivity, and symmetry that emerge from their interactions. This cannot be deduced from a single atom's behavior. In biological systems, life itself is an emergent property. Fundamental physics governs atomic and molecular behavior, but complex phenomena like metabolism, reproduction, and social organization in ant colonies arise from intricate chemical reactions and evolutionary processes. Pure physics alone cannot explain why ants build complex societies or how cells divide. Water provides a classic physical example. While hydrogen and oxygen atoms follow basic physics, water's unusual properties, expanding upon freezing and reaching maximum density at 4 degrees Celsius, emerge from hydrogen bonding networks. In ice, molecules form a stable tetrahedral structure. In liquid water, bonds constantly break and reform. This emergent behavior explains why ice floats and lakes freeze from the top. While emergent properties are rooted in fundamental physics, explaining them fully requires additional sciences. Chemistry explains molecular bonding in crystals and water. Biology addresses life's complexity, and social sciences might analyze emergent behaviors in human societies. Physics provides the foundation, but emergence shows how complex systems transcend their fundamental components. While physics serves as the foundational science that uncovers the fundamental laws governing matter, energy, and the universe, it has limitations when addressing emergent properties. These are complex phenomena that arise from the interactions of simpler components, such as how individual human behaviors combine to create societal structures. Physics can explain the physical mechanisms of neurons or brain chemistry, but it cannot fully account for consciousness, decision-making, or cultural norms. Emergent properties represent a critical gap that physics alone cannot bridge. For instance, the behavior of an ant colony emerges from simple rules followed by individual ants, or how water's properties emerge from hydrogen and oxygen molecules. In human systems, this manifests in phenomena like economic markets, political systems, and social movements, which require additional scientific lenses beyond physics. Social sciences play a vital role in this context. Disciplines such as psychology delve into individual mental processes and motivations. Sociology examines group dynamics and social institutions, and economics analyzes how resources and values are distributed through human interactions. These fields help explain why people make certain choices, how communities form, and how economic systems develop from basic human needs and exchanges. History complements these perspectives by providing the temporal dimension necessary for understanding societal structures. It examines how past events, cultural evolutions, and technological advancements shape current societies and influence future developments. Without historical context, we cannot fully grasp phenomena like institutional inertia, cultural traditions, or the long-term impacts of policy decisions. A holistic approach that integrates multiple scientific perspectives is essential for a complete understanding of reality. Physics provides the foundation, but combining it with insights from biology, chemistry, social sciences, and humanities allows us to address the full spectrum of emergent properties, from molecular interactions in living systems to global climate patterns influenced by human behavior. This interdisciplinary synthesis enables more comprehensive explanations of complex phenomena and better solutions to real-world challenges. This course provides a comprehensive exploration of physics as the foundation of physical reality. Through mathematical principles and visual demonstrations, we will examine how physics explains both natural phenomena and technological applications that shape our world. We begin with classical mechanics, the study of motion, forces, and energy in everyday macroscopic systems. This realm encompasses Newton's three fundamental laws of motion, which describe how objects move and interact through forces. We'll explore conservation principles like energy and momentum and see their applications in engineering, vehicle design, and astronomical calculations. Next, we delve into waves and fluids, exploring how oscillations and wave propagation explain phenomena from sound to earthquakes. This realm covers fluid dynamics, including how liquids and gases behave under pressure and flow, which is crucial for understanding weather patterns, blood circulation, and aircraft design. Thermodynamics focuses on energy transformations and heat transfer, explaining why engines work, why ice melts, and how biological systems maintain order. Through the four fundamental laws, we understand entropy, efficiency limits, and the direction of natural processes, with applications in power generation and climate science. Electromagnetism reveals the deep connection between electricity and magnetism, forming the foundation for modern technology. We explore electric fields, magnetic forces, and electromagnetic waves, understanding how these principles enable electric motors, generators, and wireless communication systems. Optics examines how light behaves, from reflection and refraction to the formation of images. This realm explains the workings of lenses, mirrors, and optical instruments, enabling technologies like cameras, microscopes, and the fiber optic networks that power the internet. Finally, modern physics encompasses relativity and quantum mechanics, the revolutionary frameworks that transformed our understanding of space, time, and matter. Relativity, developed by Einstein, explains gravity as space-time curvature and the behavior of objects near light speed. Quantum mechanics reveals the probabilistic nature of particles at the atomic scale, leading to wave-particle duality and quantum technologies like computers and sensors. Together, these six realms of physics provide a comprehensive framework for understanding the physical universe, from the smallest particles to the vastness of space. Through mathematical rigor and experimental demonstrations, this course will show how these principles explain natural phenomena and enable the technological innovations that shape our modern world. Classical mechanics, also known as Newtonian mechanics, is the branch of physics that deals with the motion of macroscopic objects under the influence of forces. It forms the foundation for understanding how everyday objects move, from a rolling ball to orbiting planets. This field is based on Newton's three laws of motion, which describe the relationship between force, mass, and acceleration. Developed by Isaac Newton in the 17th century, these laws revolutionized our understanding of the physical world. Newton formulated three fundamental laws that govern motion. These laws are universal principles that apply to all mechanical systems, from the smallest machines to the largest celestial bodies. The first law, also known as the law of inertia, states that an object at rest remains at rest, and an object in uniform motion continues in straight-line motion at constant speed, unless acted upon by a net external force. This is Galileo's concept of inertia, the tendency of objects to resist changes in their state of motion. In the absence of forces, objects maintain their velocity. For instance, a book on a table stays at rest due to balanced forces, but slides when pushed because the friction is overcome. The second law quantifies the relationship between force and motion. It states that the net force acting on an object equals its mass times its acceleration. Mathematically, F equals A, where F is force in newtons, m is mass in kilograms, and A is acceleration in meters per second squared. This law explains why a heavy truck requires more force to accelerate than a light car. It also shows that the same force produces greater acceleration on lighter objects. In vector form, it accounts for direction, crucial for projectile motion and orbital mechanics. The third law states that for every action force, there is an equal and opposite reaction force. Forces always occur in pairs, acting on different objects. For example, when you push against a wall, the wall pushes back with equal force. This law explains rocket propulsion, where exhaust gases push backward, propelling the rocket forward. It also governs collisions and is fundamental to conservation of momentum. In mathematical terms, if object A exerts force F on object B, then object B exerts F on object A. Oscillatory motion, or oscillations, refers to repetitive back-and-forth movement around an equilibrium position. This fundamental concept appears throughout physics, from pendulums to sound waves. Waves are disturbances that propagate through space, transferring energy without transporting matter. They can be classified as mechanical or electromagnetic, transverse or longitudinal. Wave phenomena are crucial in acoustics, where sound waves propagate through air as pressure variations, and in optics, where light waves enable vision and modern technology. Fluid dynamics studies the motion of fluids, including liquids and gases. It encompasses principles like pressure, flow velocity, and viscosity, with applications in engineering and natural phenomena. Bernoulli's principle states that as the speed of a fluid increases, its pressure decreases. This explains lift in aircraft wings and the operation of carburetors in engines. In hydrodynamics, fluid resistance affects objects moving through water, while viscosity determines how fluids flow. Surface tension creates the cohesive forces in droplets. Thermodynamics is the branch of physics that deals with the relationships between heat, work, and energy. It provides the fundamental principles governing energy transformations and the direction of natural processes. The fundamental concepts in thermodynamics are energy, heat, and work. Energy is the capacity to do work or transfer heat. Heat is the transfer of energy between systems due to temperature differences. Work involves energy transfer that can change the properties of a system, such as volume changes. The zeroth law of thermodynamics defines thermal equilibrium. It states that if two systems are each in thermal equilibrium with a third system, then they are in equilibrium with each other. This allows us to define temperature. The first law of thermodynamics is the law of conservation of energy. It states that the change in a system's internal energy is equal to the heat added to the system minus the work done by the system. This is expressed as delta U equals Q minus W. The second law of thermodynamics governs the direction of spontaneous processes. It states that heat cannot spontaneously flow from cold to hot, and that the entropy of an isolated system never decreases. Entropy, a measure of disorder, increases in irreversible processes. The change in entropy is greater than or equal to Q over T. The third law states that as the temperature of a system approaches absolute zero, the entropy approaches a minimum value, often zero for perfect crystals. This sets the baseline for entropy calculations. Thermodynamics governs engine efficiency. The Carnot cycle represents the most efficient heat engine, with efficiency given by 1 minus T cold over T hot. Real engines like the Otto cycle, used in internal combustion engines, are less efficient due to irreversible processes. Statistical mechanics provides the microscopic foundation for thermodynamics. It explains macroscopic properties like entropy through the statistical behavior of particles. Boltzmann's equation S equals K times the natural log of W, where W is the number of microstates, connects microscopic disorder to macroscopic entropy. Electromagnetism represents one of physics' greatest unifications, bringing together electricity and magnetism as two sides of the same fundamental phenomenon. This field, pioneered by James Clerk Maxwell in the 19th century, shows how electric and magnetic fields are intimately connected and propagate through space as electromagnetic waves. At the heart of electromagnetism are Maxwell's four equations, which mathematically describe how electric and magnetic fields behave and interact. The first equation, Gauss's law for electricity, states that the electric flux through a closed surface equals the enclosed charge divided by epsilon zero. This reveals how electric fields are created by charges and form closed loops around them. The second equation, Gauss's law for magnetism, shows that magnetic fields have no sources or sinks. Unlike electric fields, there are no isolated magnetic charges or monopoles. This fundamental difference explains why magnets always have both north and south poles. Faraday's law, the third equation, demonstrates that a changing magnetic field can induce an electric field. This principle powers electric generators, where mechanical motion creates changing magnetic fields that produce electricity, and it's also the foundation of transformers used in power transmission. The fourth equation, Ampere's law with Maxwell's addition, shows that both electric currents and changing electric fields can generate magnetic fields. Maxwell's key insight was adding the displacement current term, which predicted electromagnetic waves and unified electricity and magnetism completely. Maxwell's equations predicted that changing electric and magnetic fields could propagate as waves through space, electromagnetic waves. These waves travel at the speed of light and encompass the entire electromagnetic spectrum, from long radio waves used for communication to short gamma rays produced in nuclear reactions. Visible light, which our eyes can detect, occupies just a narrow band in this spectrum. Different wavelengths correspond to different colors from red to violet, and the behavior of light as electromagnetic waves explains phenomena like reflection, refraction, and diffraction that are fundamental to optics. Electromagnetic fields interact in complex ways. A magnetic field exerts a force on charged particles moving through it, perpendicular to both the field direction and the particle's velocity. This is the Lorentz force. Conversely, moving charges or electric currents generate magnetic fields around them, as shown by the right-hand rule for current-carrying wires. These principles underpin countless technologies. Radio waves enable wireless communication, microwaves heat food by exciting water molecules, X-rays penetrate soft tissue for medical imaging, and high-voltage power lines transmit electricity efficiently over long distances. Electromagnetism truly bridges the microscopic world of particles with the macroscopic world of technology. Through Maxwell's equations and the electromagnetic spectrum, we see how electricity and magnetism are unified, providing the theoretical basis for understanding light, waves, and the fundamental forces that shape our technological world. Optics is the branch of electromagnetism that examines the behavior and properties of light. Light exhibits both wave and particle characteristics, enabling a wide range of phenomena and technological applications. Reflection occurs when light waves bounce off a surface. The law of reflection states that the angle at which light approaches a surface equals the angle at which it leaves, measured from the normal line perpendicular to the surface. Refraction occurs when light passes from one medium to another with different refractive indices, causing the light ray to bend. Snell's law mathematically describes this relationship, where n represents the refractive index and theta the angles from the normal. Diffraction demonstrates light's wave nature, as waves bend around obstacles or through slits, producing characteristic patterns with bright and dark fringes. This phenomenon is crucial for understanding wave behavior and has applications in spectroscopy. Wave interference occurs when two or more light waves overlap. Constructive interference amplifies the wave, while destructive interference diminishes it, leading to the bright and dark bands seen in interference patterns. Reflecting telescopes like the one shown use curved mirrors to gather and focus light rays. This design minimizes aberrations and allows for larger apertures, crucial for detailed imaging of celestial bodies. Fiber optic cables consist of a core, cladding, and protective layers. Light travels through the core via repeated total internal reflection at the core cladding boundary, allowing signals to travel vast distances with minimal loss. Modern physics encompasses the theories of relativity and quantum mechanics, which fundamentally transformed our comprehension of space, time, and the behavior of matter at the smallest scales. These frameworks are crucial for interpreting observations that classical physics could not explain, such as the behavior of light, gravity, and subatomic particles. Relativity, pioneered by Albert Einstein, reveals that space and time form a unified fabric called spacetime. In special relativity, the speed of light is constant, leading to effects like time dilation and length contraction. General relativity extends this to gravity, describing it as the curvature of spacetime caused by mass and energy. A cornerstone of relativity is Einstein's equation E equals mc squared, demonstrating that mass and energy are interchangeable. This principle powers nuclear energy and explains how stars shine, converting matter into immense energy. Quantum mechanics governs the microscopic world, where particles like electrons behave both as waves and particles. This dual nature leads to probabilistic outcomes rather than deterministic predictions, challenging classical intuitions. The Heisenberg uncertainty principle quantifies that the position and momentum of a particle cannot both be measured with absolute precision simultaneously. This inherent uncertainty is denoted by delta x times delta p greater than or equal to h bar over 2, where h bar is the reduced Planck constant. The photoelectric effect, explained by Einstein, demonstrates light's particle nature. Photons carry energy proportional to frequency, and only light above a threshold frequency can eject electrons from metals, proving quantum theory over classical wave models. Quantum mechanics also explains radioactivity, where unstable nuclei decay probabilistically, releasing particles or energy. This probabilistic nature extends to atomic orbitals and electron configurations, forming the basis for modern electronics, medical imaging, and energy production. Einstein's theory of relativity fundamentally changed our understanding of space, time, and gravity. It consists of two main parts: special relativity and general relativity. Special relativity, published in 1905, explains how space and time are not absolute but relative to the observer's motion. It applies to objects moving at constant speeds close to the speed of light. A key thought experiment shows that the speed of light is constant in all frames. Light travels a longer diagonal path in a moving spaceship, yet takes the same time, leading to time dilation effects. Special relativity introduces several counterintuitive effects. Time dilation shows that moving clocks tick slower. Length contraction means objects shorten in their direction of motion. The famous mass-energy equivalence equation reveals that mass and energy are interchangeable. General relativity, developed in 1915, extends special relativity to include acceleration and gravity. It revolutionized our understanding of gravity, showing it as the warping of spacetime by mass and energy. In general relativity, massive objects like stars and planets curve the fabric of spacetime. This curvature creates the effect we call gravity. The more massive the object, the deeper the curvature, as shown in these illustrations. For extremely massive objects like black holes, the curvature becomes so extreme that even light cannot escape. This leads to phenomena like event horizons and singularities, where our current understanding of physics breaks down. The core of general relativity is encapsulated in Einstein's field equations, which relate the curvature of spacetime to the energy and momentum within it. These equations have been tested and confirmed through numerous experiments and observations. Together, special and general relativity have revolutionized physics, providing the foundation for modern cosmology and technologies like GPS. They show that space, time, and gravity are intimately connected in ways that challenge our everyday intuitions. Quantum mechanics governs the behavior of matter at the atomic and subatomic levels. It introduces concepts like quantization, wave-particle duality, and the uncertainty principle. Quantum mechanics is essential for understanding the behavior of atoms, molecules, and elementary particles. First, quantization means that energy and other physical properties exist in discrete, indivisible units rather than continuous values. For example, electron energy levels in atoms are quantized. Second, wave-particle duality reveals that particles, like electrons, exhibit both wave-like and particle-like properties. This is described by the de Broglie wavelength equation. Third, Heisenberg's uncertainty principle states that the position and momentum of a particle cannot both be measured precisely at the same time. This fundamental limit arises from quantum mechanics. Quantum mechanics is essential for understanding atomic structure, chemical bonding, and the behavior of elementary particles like quarks and electrons. Recent advancements in physics, particularly up to 2025, demonstrate a profound symbiosis between cosmology, the study of the universe's large-scale structure, evolution, and origins, and particle physics, which investigates the fundamental particles and forces at the subatomic level. This interdependence means that discoveries in one field directly inform and validate theories in the other, creating a unified understanding of reality from quarks to quasars. Cosmology focuses on the universe as a whole, studying its birth, evolution, and ultimate fate. Through telescopes like the James Webb Space Telescope, launched in 2021 and operating through 2025, we observe distant galaxies formed just 300 to 500 million years after the Big Bang, nearly 13.5 billion years ago. These observations provide data on the early universe's composition, temperature, and structure, which must be reconciled with particle physics models to explain how fundamental particles coalesced into cosmic structures. Particle physics, conducted at facilities like CERN's Large Hadron Collider, delves into the subatomic realm, colliding particles at near-light speeds to recreate conditions from the universe's first moments. The LHC's ATLAS detector, a 44-meter-wide, 7,000-ton instrument, detects the aftermath of these collisions, providing data on fundamental particles like quarks and the Higgs boson. This microscopic data is crucial for understanding how the universe's large-scale properties emerged from these basic building blocks. A prime example of this symbiosis is how James Webb Space Telescope data on early universe galaxies validates models derived from Large Hadron Collider experiments. The LHC recreates the quark-gluon plasma, a superhot state where quarks and gluons are free rather than bound into protons and neutrons, that existed microseconds after the Big Bang. JWST's 2025 observations of galaxies forming 13.5 billion years ago align with these models, confirming that the plasma's properties determined the universe's initial expansion rate and matter distribution, thus bridging particle-scale physics with cosmic evolution. Another critical link is the LHC's detection of rare Higgs boson decays in 2024, which validates the Standard Model's description of particle masses and interactions. The Higgs field, responsible for these masses, also shaped the universe's early expansion during cosmic inflation. By confirming the Higgs properties, particle physicists provide cosmologists with precise parameters for modeling the universe's evolution from the first trillionth of a second onward, demonstrating how subatomic measurements constrain our understanding of galactic formation and dark energy's influence on cosmic acceleration. In summary, the symbiosis between cosmology and particle physics is not merely coincidental, but essential for advancing our understanding of the universe. As of 2025, JWST and LHC data exemplify how observations at opposite ends of the scale spectrum reinforce each other, paving the way for a unified theory that explains everything from the Higgs mechanism to the accelerating expansion of the cosmos. Artificial intelligence is increasingly integrated into physics research, offering powerful tools for analyzing complex data and modeling physical phenomena. From machine learning algorithms that process vast data sets to neural networks that predict material behaviors, AI is accelerating discoveries across multiple physics domains. Machine learning, a subset of AI, excels at identifying patterns in large data sets. In particle physics, AI algorithms analyze data from the Large Hadron Collider, identifying rare events and potential new particles. For condensed matter physics, machine learning predicts phase transitions in materials, such as superconductivity or magnetism, by learning from experimental data. Additionally, AI enhances simulations of quantum systems and cosmological models, handling complexities that traditional methods struggle with. Looking ahead, hybrid quantum classical computers represent the next frontier. These systems combine the speed of quantum processors for certain calculations with the reliability of classical computers for error correction and data processing. Such hybrids could simulate candidates for the theory of everything, modeling unified theories of quantum gravity and fundamental forces. This integration promises breakthroughs in understanding the universe's deepest mysteries. The impact of AI in physics is already significant and growing. Recent surveys indicate that approximately 60% of physics research now incorporates artificial intelligence tools. In computational physics, machine learning is used in 70% of simulations, from predicting crystal structures to modeling galaxy formation. This widespread adoption is accelerating discoveries across disciplines, from new materials for technology to deeper insights into cosmic evolution. Applied physics addresses sustainability through innovative energy solutions and climate modeling. Fusion energy represents a breakthrough in clean power generation, combining hydrogen nuclei to release vast energy without greenhouse gas emissions. This technology builds on thermodynamics principles, where heat engines convert thermal energy to work, though fusion promises near-limitless power. Commercial projects are advancing rapidly, with magnetic confinement systems aiming to achieve net energy gain by the end of this decade. Climate modeling uses physics to simulate global systems, predicting temperature changes under different emission scenarios. These models incorporate fluid dynamics, atmospheric science, and computational methods to guide environmental policies. Green physics trends focus on sustainable materials like perovskite solar cells, which offer high efficiency and low production costs compared to traditional silicon panels. Their crystal structure allows superior light absorption, making them ideal for flexible, widespread solar energy deployment. Together, these applications demonstrate how physics principles drive solutions for a sustainable future. Physics increasingly informs other disciplines like biology and social sciences through multidisciplinary integration. In biology, quantum biology explores how quantum mechanics explains complex processes like photosynthesis. Plants utilize quantum coherence, where electrons exist in superposition states, allowing them to efficiently capture and transfer light energy across multiple pathways simultaneously. This wave-like behavior, rather than classical particle hopping, maximizes energy conversion efficiency, potentially inspiring new solar technologies. In social sciences, physics-based models are applied to climate economics. Principles from thermodynamics and statistical mechanics help model the economic impacts of climate change. For example, concepts like entropy and energy flow are used to analyze carbon pricing mechanisms, where economic incentives mimic physical conservation laws to optimize resource allocation and minimize environmental entropy. This approach provides quantitative frameworks for policy decisions, integrating physical constraints with human behavior and market dynamics. The broader implications of this multidisciplinary integration are profound. By applying physics to biology and social sciences, we create new fields that bridge fundamental principles with complex systems. This enhances our ability to solve real-world problems, from developing quantum-inspired medical treatments to designing sustainable economic policies. It demonstrates how physics serves as a universal language for understanding and shaping our world across all scales and disciplines. Astronomical trends in 2025 are increasingly shaped by the remarkable discovery of exoplanets, planets orbiting stars beyond our solar system. With over 4,000 exoplanets confirmed through telescopes like Kepler and TESS, these findings have revolutionized our understanding of planetary systems. Approximately 50% of these exoplanets reside in the habitable zone, where liquid water could potentially exist, raising intriguing questions about the prevalence of life in the universe. Complementing exoplanet research is the search for extraterrestrial intelligence, or SETI, which actively scans the cosmos for signals that might indicate intelligent life. Using radio telescopes and advanced signal processing, SETI programs analyze data from distant stars, particularly those with potentially habitable planets. While no confirmed detections have occurred by 2025, these efforts integrate physics principles like electromagnetic wave propagation and signal analysis, pushing the boundaries of our technological capabilities and philosophical understanding of our place in the universe. Looking ahead, future space exploration missions will provide unprecedented opportunities to test physics in extreme environments. NASA's Artemis program, beginning in 2026, aims to return humans to the moon and establish a sustainable presence, enabling experiments in low-gravity physics, radiation effects, and lunar geology. Meanwhile, Mars sample return missions planned for 2028 will bring Martian rocks to Earth for analysis, testing theories about planetary formation, atmospheric dynamics, and potential past life through fundamental physical principles like spectroscopy and materials science. The James Webb Space Telescope has transformed our view of the early universe, observing galaxies formed just 300 million years after the Big Bang at redshift values up to 14. These observations reveal that galaxies formed much more rapidly than previously thought, driven by fundamental forces like gravity, electromagnetism, and nuclear interactions. By studying these primordial structures, physicists can test theories of cosmic evolution, dark matter distribution, and the interplay between particle physics and cosmology, providing insights into how the universe's building blocks assembled into the complex structures we see today.